It's August, everybody, and soon the meteor shower of the Perseids will reach its maximum and we will see a lot of meteors. But how many? That's for us to figure out in today's session. Hey everybody, Thomas here from my channel. You see a small rebranding from my channel. I just replaced my channel name with my actual name. The reason I will mention it in the next couple of weeks. But anyway, let's start with today's session about the Perseid shower and let's take a look at some of the nice images that have been captured in the last years here from some sources like The World at Night or from NASA and ESA. You can find a lot of images in the internet of nice long-term exposures. But the question though is, how many meteors will we see? So in the media you see a lot of information coming up, like here we have like 200 meteors in this night or 150 at that night or some numbers like that. But the truth is a little bit more complicated, though not so complicated. It's, let's say, it can be put into a single Python function that helps us to determine how many meteors we can expect to see. And for this, I would say we dive directly into our Python code. As always, my code is on GitHub and you can simply click on the small badge, open in Colab, and it will immediately pop up the browser with today's code, as you will see just in a second. So this is the code from today's session, and what we are going to do is we take something called the zenithal hourly rate, the ZHR, and compute the actual expected number of meteors we want to observe, or we hope to observe. The thing is that if you read in the newspapers or on the internet about something like how many meteors you will see, the truth is a little bit more complicated. The ZHR is a very highly idealized number. It assumes that the so-called radiant, so the coordinates, the coordinate where the meteors are coming from, like for example, when it's comparable to if you're sitting in the car and it's raining and you're driving on the highway, it seems like the water drops are coming from a particular direction. This particular direction is the zenith. And if you put the the radiant, and if you put the radiant to the zenith, so the very top of the sky, 90 degrees, you get, let's say, the perfect conditions. So the ZHR assumes perfect conditions, meteors coming from the very top down, and these are all perfect parameters to get the theoretical highest number, the maximum that could be reached. But in fact, we have never a perfect situation. We have to take this theoretical concept and break it down to the number of actual observations. Now, in our script, we have 3 small cells. I start executing the very first one. And first of all, you have to set the location. So where are you? Like the latitude and longitude and also the height of your observation location. Here for me, it's Stuttgart. Then also the corresponding time zone. For me, it's Europe/Berlin. And then also the observation date time string. I put here the mid of August around 2 a.m. in the morning. Now, the Perseid radiant is also, I just grabbed it from Wikipedia. I wrote down the values here in degrees, and then you have to convert it. So 48 in radians and 58 in declination. If you don't know what these concepts mean, don't worry. I have also some videos about theoretical concepts here on my YouTube channel. And then we have something called the population index. Now, population index is a value that ranges between, yeah, let's say 2.2 to 2.6, sometimes also 2.0. We don't have to dive into this today. I would like to explain it maybe in the next session where we dive a little bit deeper into meteor science, because this is one of my favorite topics. The other thing here in the line 23 and following is, well, here are a lot of comments, is the limiting magnitude. So what is the limiting magnitude? It tells us how dark is the sky. Now, if you are in the Atacama Desert or so, you will have the perfect conditions with no, and if there's no moon, you have the perfect conditions, and it's 6.5. Now, if you're in an urban sky and the full moon is shining, you have to adjust the values accordingly. The thing is that how can you determine it? It's, let's say, pretty easy. You can open a tool like, for example, here, Stellarium. You can then compare Stellarium with the faintest star you see in your night sky, and then you see, okay, I see here the sky from this constellation. You click in Stellarium, you see the magnitude is, let's say, 4.0 or 5.0, and then you know it is like the roundabout the limiting magnitude, and then you can replace the value here as well. The other thing is something like a cloud factor, and I wouldn't just describe it as a cloud factor, but also something like the personal field of view as well. Now, if there is like no clouds at all, then we have like theoretically zero coverage. So here in this case, 1.0 means it's perfectly clear. But the thing is that our human eye is not like a fish eye lens, so we do not cover 180 degrees. I think it's more like 140 or so. And also in the vertical direction, I'm not quite sure, maybe 100 degrees or so. So you can calculate it for yourself. What is your personal field of view, and also the regions are sensitive, a little bit sensitive, depending on where the meteor strikes. But for the sake of simplicity, let's put a value of 1.0. You can also put 0.8 or something if you want to be 100% sure. Now, the zenithal hourly rate for our Perseids, there is like no value. There are values from the International Meteor organization, but here we have a very simple value extracted from the Global Meteor Network. And if we just open the link here, I think I have to copy it though first. We will see here the current shower activity, which is at around 51 meteors per hour, or the visual ZHR in the next 24 hours. Now, I think here in this case, I don't know, it was referred to the Perseids. I think it was all, but Perseids are currently the main contributor, so 51 is here the value that we can use, and I think I put here also 50. Yeah, the Perseids will be higher. I think it will be like 100, 120 or so, yeah, but let's keep it here with 50. This is our very first cell. The second cell now here defines our function, and here first of all we have to do some time zone conversion and determine the observation time, and then also convert the radiant of the Perseids into the altitude and also the azimuth angle. And of course, the thing is, if the radiant is below your local horizon, well, you cannot expect anything. It's basically zero. So yeah, I could also have write down here return equals 0. Actually, I should have done that, right? Yeah, no. Yeah, the radiant altitude is 0. Yeah, and then the of course, if I have the value later, the 0 here in this equation, the sinus of 0, then it will be 0. Yeah. So anyway, the thing is then that you will not see any meteors at all. Now, the equation itself for our hourly rate is quite simple. So the hourly rate here, I just wrote it down and broke down here also the different parameters, is the zenith hourly rate. Like here in our case, it's 50, maybe later in August 120, times the cloud factor. So if it's 1, then in our case, it's basically useless, divided by the angle of our radiant. So if it's at 90 degrees, it's 1, as you can imagine, times the population index R. You remember it was the value 2.2 to the power of 6.5 minus the limiting magnitude. So of course here as well, if the limiting magnitude is perfect, if the angle, the radiant is at 90 degrees, all these values here are 1, and our hourly rate corresponds to the zenith hourly rate. Yeah, so it's basically the same value. The truth is, of course, that our radiant altitude is not at 90 degrees, but a little bit lower. So I think in this case here, when I created the code, I think, yeah, we will see it in a moment. I think it was around 55 degrees or so. And now with the limiting magnitude of around 4, this value also has a huge impact. Now we can simply write down our equation here, just split it up into 3 pieces, and then we return the hourly rate and also the radiant altitude to give you a feeling about it. Now this is our second cell, and now the third cell. I just put it here if name equals main. So if you want to extract it to your own Python script or so, create your own little little tool out of it, we can now compute the hourly rate, the expected rate. So let's simply execute the script. The function itself contains the location, the observation time, and the time zone as an input. The other things are, let's say, like handle like constants, but you can also change it here as input functions as you like. There's like no real rule. I just want to show you the basic concept of it. Now let's go here to our values. Now our base Zenit hourly rate is 50. I just wrote it down, hard coded, and the radiant at this point will be 45 degrees roundabout. We can also then cross-check it in a moment with Stellarium, so just keep in mind the 13th of August. And then we have here the predicted results. We have the limiting magnitude of 4.0, the cloud cover is 0. And now the question is, how many meteors will we see? And in this particular case, it will reduce our meteors to 5. Yeah. So good sky conditions, but suburban light with a little bit disturbances of the moon will reduce the ZHR by an order of magnitude. This is pretty interesting to see. So the next time you see something on the internet saying, hey, you will see 120 meteors an hour in the night sky and so on, that's not the truth. The truth is that also the ZHR changes almost on an hourly level. So at the very peak, which is very sharp and small, you will have 120 or 180 ZHR. But the other parameters, as you see, they have a disadvantage factor. So they will play against us. But still, you can, I would, especially the Perseids, is always worth observing them. Yeah. So I have also some personal stories where I saw a lot of Perseids during a single night. So if you are really committed and observe for like, I don't know, 7 hours or so, you will definitely see more than 100 meteors during the night. Yeah, so that's all for the script. Now I opened Stellarium. We have here Stuttgart. Okay, not 200 meters, but 0 meters, but that shouldn't have a big impact at all. We toggle here the meteor showers as well, and I would like to change the date and time. As I said, we go to the 13th, and then it was, I think, 2 a.m. or something like that. I don't know if the script was now local time or UTC. We will see it, I think, in a moment. So let's go here around about this one. And then I will activate the azimuthal grid, which indicates the angle below the horizon. And we see here also other sources, and we can now scroll down, zoom out a little bit. And per default, they are not drawn in, or are they? Ah, the Perseids, there they are. Let's go a little bit closer, press the space bar, zooming in, and it's here 45 degrees. So yeah, it was local time. It fits perfectly with what we just computed. So the radiant is here around 45. Now, what does Stellarium tell us about the ZHR? 100. Okay, so yeah, I think it's a mean or median value. This value changes every year depending on the different streams that hit Earth. Now, if we zoom out a little bit, here are the Perseids. We can now check whether the value will improve for us, whether it goes higher. Here it's now at around 55 degrees almost. I have to check on the left side where I see the azimuth, the altitude. It's here, 51. Okay. Oh no, this was the altitude is here, 53, 60, 65. Yeah, so it improves to the morning hours. However, as I told you, the ZHR also changes during the time. So it's like a balance of different factors, but a very simple relation as you saw in the equation. So I would suggest, yeah, even if there is a small moon in the sky, we have here the moon. What is the magnitude? Okay. Yeah, it's almost full moon. I would still give it a try. Maybe you will see one fireball or the other one. So I hope you enjoyed the video, and until next time.